our next speaker is Dr. Heather Couture, a machine learning consultant and researcher and the founder of Pixel Scientia Labs, currently working with the ambitious Climate Trace project. We're absolutely thrilled to have Dr. Couture here with us today. You are already up on stage. Feel free to bring up your slides and go right ahead. Thanks so much.
My name is Heather Couture, and this talk is about estimating greenhouse gas emissions for all fossil fuel power plants globally. This work is led by two nonprofits, WattTime and Energy and Clean Air Analytics, and is funded by a Google AI Impact Award. This project has also led to the creation of a larger initiative called Climate Trace to track emissions across all sectors. Our work is focused on the energy sector. Fossil fuel power plants account for 30% of global greenhouse gas emissions. These 18,000 or so fossil fuel burning plants meet 85% of global electricity demand. While fossil fuel power is decreasing in many parts of the world, new plants are still being built in others, especially in China and India. The United States is one of the few countries that installs a continuous emissions monitoring system on every major power plant. But the costs make these systems impractical for use in many countries. They can also be tampered with or suffer technical failures. Other countries report annual emissions totals that may be rough estimates instead of actual measurements and lack verification. Averting the most severe impacts of climate change requires understanding the sources of emissions. And so we're building a system to estimate the emissions of every power plant in the world using remote sensing data from existing satellites and machine learning. Emissions estimates from this project will be made public. We anticipate a number of possible opportunities. Renewable energy developers can identify optimal locations for new wind or solar farms. Regulatory agencies can form new or updated environmental policy. Individual citizens can see how much their local power plants are contributing to climate change. And NGOs can track progress toward the Paris Climate Agreement. CO2 emissions are measured globally by two satellite missions, the Orbiting Carbon Observatory and the Greenhouse Gases Observing Satellite. They use spectroscopic methods based on the absorption of reflected sunlight in the atmosphere. However, it is difficult to distinguish anthropogenic sources, such as burning fossil fuels, from natural sources. The other challenge is distinguishing emission sources that are close together. For example, each measurement from the OCO2 satellite represents a 1 square mile area on the ground. The alternative route to global monitoring of emissions from individual sources is high spatial resolution optical imagery. We cannot measure emissions directly from satellite images, but we can infer them from signatures that are directly tied to emissions. Power plants emit greenhouse gases through a chimney called a flue stack, producing a small smoke plume. Some plants have smoke plumes that are difficult to see because they are more efficient or have pollution control equipment. So we also look for other signals from power plant cooling systems. Most plants use cooling towers or once-through cooling to cool the processed steam. Natural draft cooling towers produce a large water vapor plume that is often easy to spot, while mechanical draft disperses the water vapor more quickly, making it difficult to see. Once-through cooled plants release heat by discharging warm water to a nearby source, which can be detected by thermal infrared instruments. We create models using both visible and thermal imaging for each cooling type. We created a ground truth dataset consisting of all coal plants larger than 500 megawatts in the US and Australia. This involved joining multiple sources of data along with some manual geolocation work. While the goal of our project is to estimate the total emissions for a plant over some period of time, we started with a simpler setup, predicting whether a plant is on or off from a single image. We built a variety of machine learning models to predict the on-off status of a plant. Our most successful models focus on the flue stack and cooling signals. Using OpenStreetMap, we annotated the flue stack and cooling towers for each plant in our dataset. From each satellite image, we then extract patches around each annotation. We trained both gradient-boosted tree and convolutional neural net models using the region around the plant and the extracted patches, so 4 types of models. The gradient-boosted tree models use statistics of the pixels in the ROI or the patches. The CNN models use the full ROI or just the patches. We use transfer learning to initialize the CNN using pre-trained models from other remote sensing datasets. The patch CNN models encode each patch into a set of features. The features are then combined with an attention model that computes a weighted sum where the weights are learned by the model. We tested our models with 3 satellites over historical data from coal-burning power plants in the US, Europe, and Australia. This included 56 natural draft, 53 mechanical draft, and 35 once-through plants. Each satellite provides a different view. Sentinel-2 has a higher spatial resolution than Landsat-8 and more bands, but Landsat-8 has thermal infrared. PlanetScope has the highest resolution at 3 meters per pixel, and the most images available, as it is a constellation of hundreds of satellites. These properties contribute to the differences in performance that we see on the next 2 slides. We used 4-fold cross-validation and measured performance with mean average precision since the on and off classes are very imbalanced. The results shown here compare 4 different types of models on Sentinel-2 and Landsat-8. The patch CNN model was by far the top performer for mechanical and natural draft plants. Once-through plants are more challenging because there's no water vapor plume, and there are fewer plants of this type in our training set. Next, we obtained historical images from PlanetScope. Here, we benefit from a higher spatial resolution of 3 meters per pixel. We learned from our previous experiments that natural and mechanical draft plants performed quite differently because mechanical draft disperses water vapor much faster. So we experimented with different configurations where we trained with a single cooling technology, mechanical draft and once-through together, or all 3. Natural draft with its large water vapor plume performed the best with a mean average precision of up to 0.95. Mechanical draft and once-through benefited from combined training. While mechanical draft performed best using the patch CNN model, once-through did not gain any benefit from the flu stack annotations. We are working on some follow-up experiments to understand this. As our natural draft model has obtained results on par with human observations, we are now working on turning this classification model into a regression one to predict generation. Some challenges we face are due to natural phenomena present in satellite images. We discard 50 to 60% of images due to cloud cover, but some still get through our filters, especially for RGB imagery such as planet, in which cloud detection is more challenging. Depending on the type of cloud cover, plumes may still be visible, though it's much more difficult to rely on this signal. Snow also produces a different appearance. Multiband imagery like Sentinel-2 and Landsat-8 is better able to distinguish the plume from snow. In RGB imagery, we believe that the shadow of the plume may be a strong cue, but have not yet investigated this in detail. We look for errors by examining false positive and false negative images from our models. In the image is on the left, the plant was not generating, but a little bit of steam is visible above one of the cooling towers. We suspect that the plant shut down recently and are in the process of pulling the generation data needed to verify this theory. On the right side, these are clear examples of errors in our ground truth data. We discard such examples in training future models and prioritize plants with multiple errors for further investigation. In some cases, we found geolocation errors, 2 plants at the same site, or units missing from our generation data. Addressing such issues is an ongoing process. We also commonly experience false negatives when the plume is small or not visible. Natural draft plants are generally easier because of the vapor plume. The mist above mechanical draft units is sometimes visible, but mostly in colder weather. For mechanical draft and once through, we are largely reliant on the smoke plume and RGB images. We are also investigating thermal imagery to see if we can get a better signal. Even for natural draft plants, we experience false negatives when the temperature is high or the humidity is low because the water vapor plume is not visible. Summarizing our results for each plant, we can see that some have more accurate predictions than others. These plants show the true capacity factor plotted against the predicted capacity factor using our on-off model for planet. We are in the process of investigating the plants with poor predictions to understand if there is a systematic explanation. Overall, these results show that it's possible to achieve high-quality estimates of power plant behavior using existing satellites, an important first step toward global emissions monitoring. The next step is aggregating these predictions over some period of time, such as 1 month, and then converting generation predictions into CO2 emissions using fuel efficiency estimates for each country. We have implemented a prototype of this end-to-end model and are working to improve each component and apply it globally. We hope to expand to other greenhouse gases, fuel types, and cooling technologies in the future. Validation of our global model will be a challenge, as most countries don't release granular emissions data. However, we plan to validate at the country level and against national fuel statistics that are available for all countries. Two main challenges still exist related to the coverage of our model. Countries in our ground truth training set may not be representative of plants globally. Power plants in other countries may have different equipment or operational patterns, leading to a bias in our models. And so we continue our efforts to collect data from a more diverse set of countries for use in training or validation. The second challenge is that we are limited by the time of day of satellite observations. Visible satellite imagery is generally only available during the day, not at night. We are further limited by the sun-synchronous orbits of Sentinel-2 and Landsat-8 that observe at roughly the same time each day. This is problematic because power generation varies through the day and night. We are experimenting with visible imagery from satellites that visit more frequently and at other times of day, and with radar data from satellites that can observe at night. Ultimately, the broader our coverage, the more reliable our models will be. This project is a collaborative effort from a large and cross-disciplinary team. We are always looking for connections to relevant data and new contributors. Take a look at the website shown here for possible job opportunities in the US and the UK. You can email myself or Colin McCormick at WattTime with any questions about this project. And you can read more about the technical details in our Climate Change AI workshop paper that will be presented at NeurUps later this week. Thank you for your attention.
Wonderful. Thank you so much, Heather. Really appreciate what a great talk. And so while people are adding some additional questions to Q&A, I'm very curious, one thing you were just mentioning was that in some cases there's a fair amount of redundancy in collection times between some of the satellite images that you're encountering. I'm wondering have you thought of or tried anything with using the fact that there is redundancy between those to increase the classification performance of the algorithms? Obviously, I see the downside of it not giving you a more diverse set of times at which you're sampling, but I'm wondering if it might be able to help with classification performance for some of the challenges that you mentioned.
In some cases, we have observations from different satellites, perhaps on the same day, though there's a great diversity in how often these satellites revisit these locations. So we do take into account all the observations we have and all the observations over some period of time that we will aggregate together, for example, for 1 month to try and predict the total emissions. So all that will come into play in the aggregation model. Our focus so far has mainly been at the image level. How accurate can we predict there? Because we need to get that step right before going to the next step.
Makes perfect sense. Makes perfect sense. I see some questions coming in now. We have one here. Are you able to measure different types of emissions? Is any CO2 versus methane versus whatever else you may want to be exploring?
We're starting with CO2. We want to do the best we can with that first. We certainly hope to be able to expand to others. The largest challenge is we need ground truth data. In this case, we can convert from generation to CO2 emissions based on fuel efficiency statistics, and maybe that will apply to other greenhouse gases. But if we can get ground truth emissions data, that would be even more powerful, but challenging to get.
Absolutely. And certainly, as you mentioned, that while there may be some in the US, certainly going outside of the US seems like a very large uphill climb in some parts of the world, I'm sure.
Yeah, we're working on it. We're in contact with some companies in some regions outside the US, Europe, and Australia, but that's where our training data is focused so far.
Absolutely. Absolutely. So I see a few other questions coming in here. So are you creating any daily generation and emissions estimates, or trying to estimate anything higher frequency at this point?
At this point, our main focus is aggregating to a period of about 1 month. Longer term, we hope to be able to get some finer grain estimates, but it's going to depend on the accuracy of the estimates as to what makes sense to release. And that, of course, is dependent on the satellite data that we have and other factors in the project.
Absolutely. Absolutely. See a question here on observing coal deliveries. Can that be used to help this process of capacity factor?
We haven't looked at that one yet. We have talked about looking at the coal pile and trying to characterize changes in the pile itself. But that's a good suggestion. I'll definitely pass that one on to the team. Sure.
And I see some folks who are chomping at the bit to learn a little bit more about the methods. A question here on any publications on this work, or plans to publish at any upcoming workshops where people could dive in even deeper?
The link at the bottom of the screen to NeurIPS, we have a short paper at a workshop there. The results in that paper are outdated compared to what I've shown you here, but the methods are the same. But that's where we're at this point. I certainly hope we can release some more information about this in the future.
Fantastic. And one last question here I see. Any sense how this model varies in accuracy with the fuel source? So you talked about cooling systems, but any trends with the fuel source itself?
We've only touched on coal so far. We certainly hope to expand to natural gas and other fuel sources. There's other factors that come into play, like the fuel efficiency, the quality of the fuel, the age of the generator, all these that come into play. But so far, we've just started with coal and hope to be able to expand from there.
Thank you so much. This is fascinating work. I am eager to follow this further because I think it's since I've seen the announcement about Climate Trace and some of the work that you all have been doing, it's been extremely exciting. So let's thank Heather, and so glad you could join us.
Thank you, Kyle.